Hello, welcome to the course SJPHY1B01 Mechanics 1. The contents of this course is taken from an Introduction to Mechanics by Kleppner and Kodenko. We will continue to discuss topics from Chapter 6, Angular Momentum and Fixed Axis Rotation. In the last class we have seen that the rate of change of angular momentum is torque acting on a system. And in the case of a block sliding on a surface, we have seen that this holds true. Today let's take another physical example, a conical pendulum, and check whether this relation is valid for this scenario. So we are already familiar with this system, and there is a conical pendulum of length L and a mass m is attached to it, and it executes uniform circular motion with constant angular velocity omega. And what are the forces acting on this mass? There is weight mg acting in the downward direction, then there is tension T which is acting along the string in the upward direction. And you can resolve this tension into a horizontal and vertical component. This angle is alpha, so this is going to be 90 minus alpha. So the horizontal component is T sine alpha, and the vertical component is going to be T cos alpha. Okay. Now let's write down the equation of motion in the vertical direction. You have mg acting in the downward direction, T cos alpha acting in the upward direction. These two cancel each other, so you have T cos alpha minus mg equal to 0. So that's the reason why there is no vertical movement for this mass. The only movement is along this horizontal plane. Okay. So since these two forces cancel, the only force which is acting, or the net force which is acting on the mass, is the horizontal force, which is minus T sine alpha. Minus sign indicates that this acts inward direction. So the net force is going to be F is equal to minus T sine alpha r cap. So if you recollect, for any object executing a circular motion, the net force which is acting on it is nothing but the centripetal force. So this force is the one which provides the centripetal acceleration required for this circular motion. And as you know, centripetal force always acts in the inward direction. Okay. Now we need to calculate the torque about point A as well as point B, which is the pivot point. So we have done this exercise for the calculation of angular momentum. There we have seen that angular momentum about point A, LA, is mr square omega, and it's a constant with respect to magnitude as well as direction. It is consistently along the plus z direction. And similarly, about the pivot point B, the angular momentum LB is mLr omega. Here the magnitude is a constant, but the direction changes. Okay. Now let's first take point A. So the position vector, or the distance vector, you call it as RA. And the torque about point A, tau A, is nothing but RA cross F. But RA is nothing but the R vector, which you can write it as R cap, where R is the magnitude of the R vector. And this is the force. So if you notice, both force and RA are along the R cap direction. So you are talking about cross product of two parallel vectors, which is going to be 0. And the expression for angular momentum we already know from the previous class. This is mr square omega k cap. Here m is a constant for circular motion, radius is a constant. For uniform circular motion, the angular velocity omega is a constant. All these are constants, so when you take dLA by dt, that's going to be 0. So tau A equal to 0, dLA by dt equal to 0. So you have shown that tau A equal to dLA by dt. Now what about tau B? So this is the pivot point. So here the the distance vector is RB, whose magnitude is L. And once again, torque is nothing but the moment of force, so tau B equal to RB cross F. Let's first look at the magnitude of tau B. So RB you can resolve into a parallel component and a perpendicular component, and cross product with the parallel component is going to be 0, so you need to bother only about the perpendicular component. So as you can see, this is the force, this is the perpendicular component. Since the angle is 90 degree, the cross product is going to be replaced by a normal product of the corresponding magnitudes. So magnitude of the perpendicular component is going to be L cos alpha, because this length is L, this angle is alpha, so this side, the perpendicular component is L cos alpha. So magnitude of tau B equal to L cos alpha F, and we have seen that F is minus T sin alpha r cap. When you look at the magnitude, it is T sin alpha. So substitute for F, so you get magnitude of tau B equal to L cos alpha T sin alpha. But from the vertical equation of motion, you know that T cos alpha equal to mg. So in this expression, you substitute for T cos alpha. So you get mgl sin alpha. Now, what is the direction of tau B? So this is a cross product. Place your right hand along the direction of RB and curl it towards F, and you will find that your thumb is pointing in the tangential direction. So tau B is along the tangential direction given by theta cap. So tau B vector equal to mgl sin alpha theta cap. Now, what about angular momentum? We have derived this result in the previous class, and the moment of the magnitude of angular momentum LB equal to mLr omega. And this is the angular momentum vector LB, and since this is at an arbitrary angle alpha, you can resolve into a parallel component LR and a perpendicular component LZ. So from this geometry, you can see that Lz equal to mLr omega sin alpha, which is the vertical component, and the parallel component Lr is going to be mLr omega cos alpha. So as we have discussed in the previous class, the vertical component is a constant with respect to magnitude as well as direction, whereas the horizontal component, its magnitude is a constant, but its direction changes. So that's what happens when the mass rotates along a circle, right? The magnitude remains a constant, but each point the direction is going to be different. Okay. So I can write LB as a vector sum of these two components. So that's what I'm going to do here. So if you look at the direction, Lz is going to be along the z direction given by k cap, and Lr is going to be along the r direction given by r cap. So I can write LB equal to mLr omega sin alpha k cap plus mLr omega cos alpha r cap. Now what about dLB by dt? As I said, the vertical component, this is constant with respect to magnitude as well as direction. So when you take its derivative, it's going to be 0. And the second term, all these components are constants, m, l, r, omega, cos alpha. The only thing which varies is the direction of r cap. So dLB by dt equal to mLr omega cos alpha dr cap by dt. From the first chapter, we know that dr cap by dt is nothing but theta dot theta cap. Theta dot is angular velocity omega, so dr cap by dt equal to omega theta cap. Now make this substitution in this equation, you get dl omega by dt equal to mlr omega square cos alpha theta cap. Now as I said, The radial force is nothing but the centripetal force. This is the one which provides the centripetal acceleration required for the circular motion. And I know the expression for centripetal force. This is mv squared by r. So I can write T sine alpha equal to mv squared by r. Or in terms of angular velocity, I can write it as mr omega square, because linear velocity v equal to r into angular velocity omega. V equal to r omega. Okay. So in this expression, instead of mr omega square, I can write T sine alpha. When I do that, I get dLb by dt equal to L cos alpha T sine alpha theta cap. Once again, instead of T cos alpha, I can write mg. So now my expression becomes dLb by dt equal to mgl sine alpha theta cap, which is nothing but the expression for tau b. So we have shown that tau b equal to dLb by dt. So with these two examples, we have established that this is a general result. So in the case of any physical system, the rate of change of angular momentum is going to be the torque. In some systems, the torque is generated due to gravity. And what's the expression for that? So let's solve a problem. Find the torque on a rigid body of mass m about origin A when the applied force is due to a uniform gravitational field G. So we have a rigid extended body. It's going to be difficult to analyze the body as a whole. So what we do, we assume that it's made of a large number of particles, and we are going to analyze each particle one by one. Okay. So I'm going to choose the jth particle. Let mj be the mass of the jth particle. Let rj be its position vector with respect to origin A. Then the torque acting on the jth particle tau j is going to be r cross f. Here, since only gravitational force is acting on the system, force F is equal to m into g. So tau j equal to rj cross mj into g. So this is for the jth particle. Similarly, you can calculate torque for each particle. Find the sum of all this, you get the total torque. So total torque tau equal to summation over j tau j, which is summation over j rj cross mj g. Since m is a scalar, it doesn't matter whether you keep it on the right side or left side of the cross product. So I'm going to take it to the left side. And g doesn't have a subscript. It is common for all the terms. So I can take it outside the summation. When I do that, I get summation over j mj rj cross g. From the definition of center of mass, we know that summation over mj rj equal to m into r, where capital M is the total mass of the system, capital R is the position vector of the center of mass, right? So in this expression, instead of summation over mj rj, I can write mr. So tau equal to mr cross g. So once again, m being a scalar, I can place it on any side of the cross product. So this is equal to r cross mg, where mg is the total weight of the system. So tau equal to r cross w. So torque due to gravity is nothing but a cross product of position vector of the center of mass and the total weight of the system. One of the biggest applications of angular momentum is in the analysis of general motion of a rigid body. As I said in one of the previous classes, there is an important theorem in classical mechanics known as Chasel's theorem, which says that any general motion of a rigid body can be decomposed into two components. One is a pure rotation, second one is a pure translation. So understanding of angular momentum is important in delineating the mechanics of motion of a rigid body. Now, a general rotation motion is going to be a difficult choice to start with. So, for the sake of simplicity, we will take a special type of rotation motion known as fixed axis rotation, which is easy to analyze. Okay, so we will start with a simpler case. Once we are thorough with our concepts, we can move on to more challenging problems. Now, what's the meaning of fixed axis rotation? So here the direction of the axis of rotation is always along the same line. The axis itself may translate, but its direction doesn't change. For example, look at the wheel of a moving car. If the car is moving along a straight line, then the axis of rotation is always going to be perpendicular to the plane. So this is the example of a fixed axis rotation. On the other hand, if this car takes a turn, then understandably the axis of rotation is going to change its direction, right? In that case, it doesn't become a fixed axis rotation. Okay. Now we are going to talk about fixed axis rotation of rigid body. By rigid body, what I mean is that when a body rotates, its shape doesn't change. Or when a rigid body rotates about an axis, every particle in the body remains at a fixed distance from the axis. If this is not true, what happens? The shape is going to change. Okay. So once again, we are going to assume that the rigid body is made of large number of particles, and we are going to analyze each particle one at a time. So I am at the jth particle. Let mj be its mass and rj be its position vector with respect to the origin. And let Vj be its velocity, linear velocity, and let me assume that the axis of rotation passes through the origin. Then rho j is the perpendicular distance from the axis of rotation to the particle. Okay. Now, if we choose a coordinate system with its origin lying on the axis, then for each particle in the body, the magnitude of the r vector is going to be a constant. So whether mj is at this point, this point, this point, this point, everywhere, when you look at the position vector rj, its direction is going to be different, but its magnitude is going to be constant. Now the only way r vector can change while its magnitude remains a constant is that the velocity is perpendicular to r. If velocity is not perpendicular to r, what happens? Then, as always, you can resolve the velocity into two components, a parallel component and a perpendicular component. Now, the parallel component of the velocity is going to create a change in the magnitude of the r vector, right? If both are along the same direction, r is going to increase. If both are along the opposite direction, then r is going to decrease. Then that is common sense. So if the magnitude of r is constant, that means that there is no velocity component along the direction of r vector, and the velocity component is completely perpendicular to the r vector. So this is the case of a pure rotation, right? In the case of pure rotation, r and v are perpendicular to each other. Now with this understanding, I can try to derive a general expression for angular momentum of a fixed axis rotation. Now first, the linear velocity, magnitude of linear velocity Vj is nothing but rate of change of position vector, which is drj by dt, or in terms of angular parameters, I can write as linear velocity equal to the perpendicular radius multiplied by angular velocity. Here perpendicular radius is rho, so this is omega rho j. Usually for radius we use the notation r, but here we have already chosen r for position vector. That's why we are using a new symbol rho for the perpendicular distance. So don't get confused with this new notation. Okay. And from the geometry it's clear that rho and r are completely different, because rho is something related to this planar motion, the circular motion in this xy plane. So rho will have only x and y components. Since this is a circle, rho j is nothing but square root of xj square plus yj square. On the other hand, r is the position vector in this x, y, z domain. So any general r vector can be written as square root of x square plus y square plus z square. Okay. Now, angular momentum of the jth particle is given by L of j equal to Rj cross Mj Vj. If you are talking about rotation in the xy plane, so if you look at the direction of Vj, this is in the counterclockwise direction. So we know that angular momentum is going to be along the plus z direction or along the axis of rotation. Okay. So the component of angular momentum along the axis of rotation, I call it as Lz of j. This is nothing but, from the first class we know that angular momentum is linear momentum multiplied by the perpendicular distance, or distance multiplied by perpendicular linear momentum. You can choose anything. So let's choose the first definition. It's linear momentum multiplied by perpendicular distance from the axis. And perpendicular distance is nothing but rho j. So I can write Lz of j equal to mj vj rho j. But Vj is omega rho j. When you make this substitution, you get Lz of j equal to mj rho j square omega. So this is the z component of angular momentum for the jth particle. So what about the total z component? You take summation over j. So you get total Lz equal to summation over j Lzj, which is summation over j mj rho j square omega. Now this term, summation over mj rho j square, is known as moment of inertia I. So in terms of moment of inertia, I can write angular momentum Lz equal to I omega. Now moment of inertia is a parameter which is equivalent to mass in the case of linear motion. As you know, for every linear parameter, you have a corresponding angular parameter. So in linear motion, you talk about change in distance r. In angular motion, you look at change in angle theta. You have linear velocity v, you have angular velocity omega. You have linear acceleration, similarly angular acceleration. You have linear momentum p and angular momentum L. Right? So for every linear parameter, there is a corresponding angular parameter. So moment of inertia is the angular equivalent of mass. So if you look at the expression for linear momentum p equal to mass m into linear velocity v. So you simply change the parameters with the corresponding angular parameters. Instead of p, you have L here. Instead of m, you have I here. Instead of linear velocity v, you have angular velocity omega here. But there is one fundamental difference between mass and moment of inertia, because mass depends only on the amount of substance in a system, whereas from the definition it's clear that moment of inertia depends on amount of mass as well as the distribution of the objects. Now, this equation is valid if you consider that the system is made up of a large number of individual particles. On the other hand, if you take an extended system like a disk or a ball, you have a continuous distribution of masses. So in such cases, it's going to be difficult to do a summation because you are essentially talking about an infinite summation. In such cases, it makes more sense to write down equations in the form of an integral, because an infinite summation is nothing but an integral. So summation over j mj rho j square is it can be written as integral rho square dm, where dm is a mass element. So in terms of the integral equation, the expression for moment of inertia becomes integral rho square dm. Rho is nothing but the square root of x square plus y square. So moment of inertia I equal to integral x square plus y square dm. Since mass is density into volume, typically instead of writing it as dm, we write it as a product of density and volume element. So let's assume that the density of the mass element dm is w and the corresponding volume is dv. So I can write dm equal to w dv. Once again, the notations are not very intuitive in the reference book, because typically people use the symbol rho for density, but since we have already chosen that symbol for perpendicular distance, we are using a new symbol w here. Okay. So don't bother about the notation much, as long as you are clear about the underlying physics, that will do. Okay. So dm equal to w dv. So now my expression for moment of inertia becomes I equal to integral rho square dm, which is integral x square plus y square w dv. So in the next class, what we are going to do is we will take some simple objects and find out their angular momentum. So if you have objects with regular shape and noticeable symmetry, the calculation of moment of inertia is going to be a simple, straightforward job. So we will do a couple of examples in the next class. Thank you.